Welcome to this video, Parallelograms Part 2. In this video, we will define different types of angles, including the angles that form when a line crosses two parallel lines, and we will consider special cases of the parallelogram. If you are new to the concept of parallelograms, please watch my previous video, Parallelograms Part 1. I will put the link to this video in the description box. And please don't forget to subscribe to the channel to receive notifications for the new videos I upload to the channel. Now let's start. So we will define different types of angles, including the adjacent angles. Two angles are adjacent if they share a common side and a common vertex and they do not overlap. For example, we can see that here we have these two angles that are adjacent to each other. They share a common vertex, a common side, and they do not overlap. On the other hand, for example, we can see that these two angles overlap, so they are not considered to be adjacent. We can notice that this big angle contains the smaller one. Now, the complementary angles. Two angles are complementary if the sum of their measures is 90 degrees. Here we have got two examples. The first example, you can see clearly that those two angles are adjacent. They share this common side and a common vertex. And you can see here that they add up to 90 degrees. However, it's not necessary for two angles to be complementary that they are adjacent. For example, here we have two angles with the same sizes as these ones we have here, but they are not adjacent. However, their sizes add up to 90 degrees. So we consider them to be complementary. Now, the supplementary angles, two angles are supplementary if the sum of their measures is 180 degrees. Similarly, we can see here two adjacent angles, and they add up to 180 degrees. However, they might not be adjacent to be considered supplementary angles. For example, here we have this angle has the same size as this, and that angle has the same size as this. So if we add the two sizes of this angle and this angle, we will find the sum to be 180 degrees, although they are not adjacent. So here we have a note that angles on a straight line add up to 180 degrees. So we have these three angles, let's say. We can notice that these three angles fall on a straight line. So in this case, no matter how many angles we have, their sizes will add up to 180 degrees. We might have also additional angles here and there. We can notice if we added the sizes of all these angles, they will add up to 180 degrees. Lastly, the vertical angles. Vertical angles are the angles that are opposite to each other. When two straight lines intersect and their measures are equal. So here we have these two lines intersect and result in these two angles here that are opposite to each other, and they have equal sizes. also we have these two opposite angles, and they have also equal sizes. Now, let's move to discuss the concept of two parallel lines and the line that crosses them. So here we have the line delta. It crosses the two parallel lines delta 1 and delta 2. So when this line crosses these two parallel lines, we have these 8 angles that are formed. So let's start by the alternate interior angles. And for an example, we have A3 and B1. So those two angles, A3 and B1, are alternate interior angles, and they have equal sizes. Similarly, we have here A4 and B2 are alternate interior angles, and they also have equal sizes. Now, let's move to the alternate exterior angles. For example, A1 here and B3 are two alternate exterior angles, and they have the same size, as well as A2 here and B4. They are also alternate exterior angles, and they have the same size. Now, the corresponding angles, they also have equal sizes. For example, first let's remove the annotations. Okay, so for the corresponding angles here, we have A2 and B2. So A2 here and B2, they are two corresponding angles, and they have equal sizes. We have also A3 here and B3. We have A1 and B1. Also, we have A4 and B4. And in an opposite manner, if we have a line delta that crosses two lines, delta 1 and delta 2, while we don't know that delta 1 and delta 2 are parallel to each other, and we want to prove that, how do we do that? Delta 1 and delta 2 are parallel if any of the following is satisfied. Two alternate interior angles are equal. For example, if we could prove that A4 and B2 are equal, or A3 and B1 are equal, we conclude that delta 1 and delta 2 are parallel to each other. Another case in which delta 1 and delta 2 could be parallel if we could find two alternate exterior angles to be equal. For example, if we could prove that A1 and B3 are equal, or let's say A2 and B4 are equal to each other, then we conclude that delta 1 and delta 2 are parallel to each other. And the other case, the last one, by which we can consider or conclude that delta 1 and delta 2 are parallel to each other, if we could find two corresponding angles to be equal. For example, if we could prove that A1 and B1, that are two corresponding angles, are equal, or A4 and B4, or A2 and B2, or A3 and B3. We will take some examples to try to prove that two lines are parallel to each other based on the fact that we could find two angles that are equal to each other, and they satisfy one of the following: either they are alternate interior angles, or alternate exterior angles, or corresponding angles. So here, prove the following: consecutive angles in a parallelogram are supplementary. So here we have CB, HD is a parallelogram, and we want to prove, for example, that C plus D is equal to 180 degrees. For this reason, and as we see here, we can extend DC. Okay, so now we have the angle DCB, and the angle BCA fall on a straight line, so they add up to 180 degrees. So the sum of their sizes is 180 degrees. However, we know in a parallelogram that CB is parallel to DH. This means that the straight line AD crosses CB and DH and forms two equal corresponding angles, which are HDC and BCA. These are equal in size because they are corresponding angles. From this and that, we replace BCA here. Since it's equal to HDC, we replace BCA here with HDC. So we conclude that from here, DCB plus HDC is equal to 180 degrees. So DCB and HDC, or in other words, C plus D is equal to 180 degrees, which is required in the question. Now we remove this solution in order to solve the other exercise. Okay, so we have this shape here. We have three parallel lines. These two lines are crossed by this line and these two parallel lines also are crossed by this line, and we want to calculate A. How do we do that? So first of all, we can notice that this line, let's call it delta 1, this one, crosses these two lines. Let's call them K1 and K2, here K3. So delta 1 crosses K1 and K2. So since they are parallel to each other, we conclude that this angle is equal to this angle because they are two corresponding angles. Similarly, we can notice that delta 1 and K1 cross each other. It means that 135 here is equal to this angle since they are vertical angles. Okay. And now we have this angle here and the 135, they fall on straight lines, so they are supplementary. From this, we conclude that this angle is equal to 180 minus 135, and this gives us 45 degrees. Now, we have just mentioned that this angle is equal to that one. It means that this one also is equal to 45 degrees. Now we need to calculate this one, the small angle here between K1 and delta 2. K2 and delta 2. How do we do that? Similarly, here we have 135 and this angle here are supplementary. So this angle here is equal to 45 degrees. And this angle here and this angle here are equal to each other since they are two corresponding angles, because the line delta 2 crosses the two parallel lines K3 and K2. So this will also be equal to 45 degrees. From there, we conclude that the size of A is equal to 45 degrees plus 45 degrees, which is 90 degrees. When do we say that a quadrilateral is a parallelogram? We say that a quadrilateral is a parallelogram if any of the following is satisfied. If every two opposite sides in the quadrilateral are parallel, and this is actually the same definition as the definition of the parallelogram. It's a quadrilateral in which every two opposite sides are parallel to each other. The other case by which we can say that some quadrilateral is a parallelogram is if the two diameters in the quadrilateral meet in a point that falls on the middle of each diameter. So we have to prove that the point M splits each of the diameters BC and AD in our case into two equal parts. So length of AM is equal to the length of MD. At the same time, the length of MB is equal to the length of MC. And the third case by which we can say that some quadrilateral is a parallelogram, if we could find two opposite sides in the quadrilateral that are parallel and have the same length. In our case, for example, if given a certain quadrilateral in which AB is parallel to CD and the length of AB is equal to the length of CD, then we can conclude that this quadrilateral is a parallelogram. Special cases of the parallelogram. We will be looking at the rectangle, rhombus, and square. So let's start by the rectangle. A parallelogram is a rectangle if any of the following is satisfied. So here we have a parallelogram. The first thing is the measure of an angle is 90 degrees. So if we find a parallelogram by saying that every two opposite sides are parallel to each other, so that AD is parallel to BD and AB is parallel to DC, and if we could find at least one angle which is equal to 90 degrees, for example here B, then we can say that this parallelogram is a rectangle. The second case by which we can say some parallelogram is a rectangle is when the length of the two diameters are equal. So here we have a parallelogram in which the length of DB is equal to the length of AC. In this case, we conclude that this parallelogram is also a rectangle. The second case is the rhombus. A parallelogram is a rhombus if any of the following is satisfied. First, if the length of two adjacent sides in the parallelogram are equal. For example, here we have ABCD is a parallelogram in which two adjacent sides, which are AD and B and AB, those two sides have equal length. Then we conclude that this parallelogram is a rhombus. The second case by which we can say that a parallelogram is a rhombus if the diameters of the parallelogram are perpendicular to each other. So here we have a parallelogram in which the diameters DB and CA are perpendicular to each other. In this case, we can conclude that this parallelogram is a rhombus. The third case, if we have a quadrilateral, if we note that all sides have the same length in this quadrilateral, then the quadrilateral is a rhombus. So in this case, we can move directly from the quadrilateral to the rhombus. The last case is the square. The square is a rectangle in which two dimensions, length and width, are equal. So here we have a rectangle. We can notice that it's first a parallelogram, and then it's a rectangle, since at least one of the angles is 90 degrees. Now, if we can prove that or see that the length of the rectangle is equal to the width of the rectangle, or in other words, the lengths of two adjacent sides are equal to each other, then we could say that this rectangle is also a square. The other case, we can define a square. It's a rectangle in which the two diameters are perpendicular to each other. So here we have a rectangle ABCD in which the two diameters are perpendicular to each other. In this case, it's also a square. Now, how can we move from the rhombus to the square? We say that a rhombus is also a square if we could find at least one angle with the size 90 degrees. So here we have ABCD is a rhombus. We can notice how the lengths of all sides are equal to each other. Then if this rhombus contains one angle with size 90 degrees, we can conclude that it's also a square. A rhombus is also a square if we could prove or see that two diameters have equal lengths. So here we have ABCD is a rhombus in which we can see clearly that the lengths of all sides are equal to each other. Then in this rhombus, if we could prove or see that the length of AC is equal to the length of DB, then we can conclude that this rhombus is also a square. Thank you for watching this video.